So welcome everyone to another edition of KmerAI Talks. Yeah, so today we're going to talk a little bit about protein applications of machine learnings in protein designs. And our speaker today is Loïc Kwate Dassi. And from what I've seen, he's a former student from Polytechnic Yaoundé, and he also did like an internship at IBM, and is currently working as a research engineer at DeepMind. So without wasting more time, I just give him the floor. And I think like currently like the approach we've been using in the past few sessions is just present, and then at the end we take the questions. So just go through your presentation, then at the end we're going to have the interactive sessions with the questions and answers. So it's up to you now, Loic.
Thank you, Ulrich, for giving me the floor. And hi, everyone. As Ulrich said, my name is Kwate Dassi, and I am currently a research engineer at DeepMind, working on quantum chemistry and AI. I'm very pleased to be here to share one of the work I've been doing in the past with my colleague when I was at IBM. And one thing I would like to stress out before starting is it's been at least 3 or 3.5 years that I work on this. So things are not fresh in my mind as they were before. And so there are some details that might slip my mind. So if I said something wrong, just let me know. Like the domains in which I work has significantly shifted over time. So yeah, but I think the pinnacle of the presentation will be there. So this work has been conducted when I did my internship at IBM. So I should also mention that the other authors, so I wasn't alone when doing this. So so basically, during the presentation, if we want to have a short summary, we'll be talking about how we can leverage the language model to identify the binding site on enzymatic proteins, and we'll basically see how we can use the language model and how this could be useful for other downstream tasks or other in the industry, how such a model can be useful. So let's start with the fundamentals, which is the attention mechanism. So if we are to define the attention mechanism, I will probably say, like, if we want to start from something simple, I will say the attention mechanisms is a mechanism through which different parts of the input interact to solve a problem. And here, solve a problem is a generic way of phrasing a goal. Like, it could be if you are in a language model, or like, let's say you want to minimize a loss for something. So this is what I call solve a problem. So the problem here means the objective goal of your task, and then the attention mechanisms is just mechanisms through which different parts of your input will interact in order to solve the goal that you have set beforehand. And through the past decade, and as we are saying it now, the attention mechanism is widely used in sequence modeling. And in general, the task, like the generic task we will try to use with the attention mechanisms are the next token prediction, the mass language modeling, and there are other several tasks in language model that we can use the attention mechanism to solve. But broadly, in the sequence modeling, um, just to name a few, these are the tasks that we can use. Like these are the tasks that we can solve with the attention mechanisms. And at the beginning, like in 2012, the attention mechanisms was widely used for the language task, but what we saw near 2018 is that um, people started phrasing tasks in computer science as, let's say, if we divide an image into patches and we're interested in predicting the next patch. So in that sense, we can also see the image as a sequence of patch, and we apply the same mechanism as in sequence modeling to solve this task. So we've been seeing people using the attention mechanisms for like the next patch prediction or the mask patch prediction. And also now we are seeing people not only using the attention mechanisms in uh, either sequence modeling or to process image, but we also see it in different domains, like as what we will be discussing, like in proteins, in like basically when you frame your input in a sequence of items, then you can be interested in processing this sequence of items with the attention mechanisms. So once you do that, people have been interested in seeing basically when you train a model using the attention mechanism, how we can leverage the information that is encoded in the attention in the attention mapping of the input, like in the input, and see if we can extract all the information, like in as we saw, like as we're seeing in the right hand figure. This is only one showcase where um, there are some authors that try to train a machine translation model and with the attention mechanisms. And after the training, they were interested in seeing if there is a correlation between the output and the input through the lens of the analysis of the attention mechanisms. And this is only one of the interpretation. So this dates back to some years ago, but now there are other people trying to use other interpretability method. But one way to also probe the information learned by the model is to go through the attention mechanisms, go through the attention mapping between the inputs and see if some correlation can be deduced from this. And now let's dive into the concrete topic we'll be discussing. So we are trying to, like, the main aim of the project is to see if using language models we can predict the binding site of a protein. So basically, let's start from the beginning. I'll take an example, like generally in biology, scientists will describe a disease with proteins. Just to stress out, this is not my domain of expertise. So if I say something wrong, just let me know. But I think the main point is there. So in general, to identify the disease, we'll have a proteins. And when we want to solve that disease, in general, the scientists will design small molecule, and the small molecules here are the substrate, and they are intended to interact with the enzymes, which is the proteins. And the interaction between the enzymes and the substrate will happen on specific site of the protein, which is the active site or the binding site. And so when the small molecule and the proteins will interact, the interaction will happen in active site. And then basically the enzymes will, like each substrate will be located on a specific pocket on the enzymes. And then the enzymes will bend itself to make the substrate close geographically such that they can interact. And after the interaction, the enzymes will recover its original shape, and at the end, we will have the product. So when we want to characterize the function of a proteins, we are generally interested in the active site of that protein, because when we know the binding site of the proteins, in we can use this information to know what kind of molecule can be easily bound with that enzymes. So knowing this information is useful to design, for example, the drug, I mean, the molecules that we can use to solve disease. So the active site are actually critical information to describe a protein. And now we talked previously about the proteins and the substrate. There are different representation that we can use for the proteins, and in general, like when we talk about the proteins, they are the compound of small, like we start with the atoms, and then we compound atoms, and then we have a molecule. When we keep compounding the molecule in a specific way, we'll have a chain of molecule. Like we can say each molecule as an amino acid, and then when these amino acids are chained in a specific way, we'll have a long sequence of this amino acid that we call the proteins. So in the first row, we have an example of how we can represent a proteins. It's just the sequence of its amino acid, like CG, G, T, C, and A. And this is a one-dimensional representations of the proteins. And we could also be interested in the three-dimensional structure of the proteins. So one way to represent is just to have a one-dimensional amino acid sequence, and we can also have the three-dimensional structure. So let's say if we have the first row, what is the actual coordinate of each atom in the proteins? So in this is another way of representing the protein. So basically, we will have the three-dimensional coordinate of each atom in the proteins. And then we previously talked about the substrate. These are just small molecule. And then one way to represent the small molecules is just to have the small representation. So basically, we have all the atoms. This is a convention, like a nomenclature to describe this small molecule. And there are many other ways to represent these structures, but in this work, we will basically focus on three representations. The first is the amino acid sequence, because we will be dealing with the sequence of information. So we will treat the amino acid sequence as a kind of language describing the proteins. And for the substrate, we will consider the small representation, which is just the sequence of the atom in that small molecule. And we will also use the three-dimensional structure of the proteins to show that we can, like from the language model, we can extract the three-dimensional information of the proteins from the one-dimensional amino acid sequence. And now let's dive into the core of the work we've been doing. So the basic question we try to answer is, given given an amino acid sequence, we want to figure out the binding site of that proteins. So how do we proceed? Like we start by collecting a bunch of reactions. So basically, the reaction here is the reactant, the enzymes, and the product. So here in the first figure on the left-hand side, we'll have a molecule with some blue, gray, and red dot, which is the reactant. In the middle, we will have the enzyme that will catalyze the reaction. And on the left-hand side, and on the right-hand side, we will have the product of the reaction. So the reactant on the left-hand side will be represented with its small representation, which is the first chunk that we have in blue here. And then the enzyme will be represented with its amino acid sequence. And the product will also be represented with its small representation. So we did this, we collect several reaction, and then we train a language model using a mass language modeling. So basically, you can consider the sequence under the first image as one sentence in your data set. And then the language model task is basically, we want to, we mask some chunks of that reaction, and we want the language model to reconstruct the masked tokens. So basically, this is just a mass language modeling task, and we use a language model to do that. And One thing that we found interesting is we like, given that we consider this as a language, we need a vocabulary. Like in the common language, we'll have English or French. We'll have a subset of syllables like the word. Basically, if you have a text, you need a way to tokenize that text such that the model can process it. So we did the same here. We needed the basic units of information that will be processed by the model. So to do that, we had basically two tokenizers. We didn't use the same tokenizer for the reactant and the enzymes. So for the reactants and the product, we use the same tokenizer because we can say the language is the same. Like the vocabulary here is the same. But for the amino acid sequence, the vocabulary is not exactly the same. So we fit a byte pair encoding tokenizer only for the amino acid sequence to build a vocabulary for the language describing the amino acid sequence. So we had two tokenizers, and for different part of the reaction, we tokenize with its corresponding tokenizer. And after this, we train a language model until we reach a good level of perplexity. And now the question we try to ask is, uh, the language model we use the attention mechanism, and then we wanted to ask if a model is effectively able to reconstruct the mask part of of the enzymatic reaction. Is that model like, when we probe the attention mechanism learned by that model, could we extract information um, on where the reaction happened? So basically, if let's say we take the first atom on the left hand side, which is N, and we want to see, I'm sorry, and we use the attention mechanism. So we basically look at the attention matrix of this atom and some chunks of the amino acid sequence. So we want to see if this attention mechanism, like if this attention weights encode actually the active site of where the reaction happened. So yeah, this is following what I was saying. After training, using an unsupervised method, like basically we didn't train the model specifically to recognize the active site, but we trained the model to reconstruct the reaction, and then um, we go through the layers of the model and also the head. Like for the attention matrix, learn by, let's say, the layer, because we use a transformer. Like for the attention matrix of, let's say, the layer 1 and the head, um, let the layer I and the head J, we look at the interaction coefficient, if I will say, of one atom and one chunk of the amino acid sequence. We look basically at the weight. Like we care about if these weights will contain the information on the active site. So we do this for all the atoms of the reactant, and we basically save all the chunk of the amino acid sequence that has a strong, like that have a strong attention coefficient. And we wanted to look at if this sequence of amino acid sequence corresponded to the actual active site. And one thing that is impressive about this is like, one thing that is counterintuitive is we train a model on a one-dimensional information, and we are asking the model the information about the three-dimensional. So one thing that we try to do is, like, after the prediction of the active site, we want actually to visualize, like, let's say we go through the attention mechanism analysis, and then we have the sequence that the model predicted as the active site, and we want to actually see if there is an overlap between what the model has predicted and the ground truth active site. So basically, what we did is first we had to find a ground. Basically, we had the ground truth. Like in the database that we use, we had the actual active site of the given proteins, and there is also a database containing, like, we can use like there's database pfarm that contain the homologous sequence of the protons. So we use this as the baseline. And in this figure, just to describe, this is the three-dimensional representation of the protons. So in white, we have, I would say, the background of the molecule of the protons, and in blue, like in dark blue, there are actually the binding site, the binding site of the protons, and then where like wherever we have a grain is where we have the overlap between what the method that we use predicted as the active site, and where we have a red, there are the error. So basically the model predicted this as the active site, but they were not actually the active site. So as we can see on the left hand side, we basically compare two baseline method, and on the right hand side we compare our method, which is RxNAA mapper, and the plib is one statistical method that has been created by some authors to um, predict the active site given only the sequence. So as we can see here is, despite the fact that the model makes some error, we are actually able to have some overlaps between what the model actually predicted and the ground truth active site. And the other interesting things that we try is when you have the predicted active site, it's not all the job, because you need to actually do the binding. It's like, let's say you have the active site. One thing you need to make sure, like, you have the predicted active site. One thing you need to make sure is, if you use that predicted active site as the actual active site, what is the energy that you will obtain if you consider this as the active site? So one thing we tried is, given a substrate, like if I go back to the previous figure here, so let's say we have the predicted site. So given a substrate, we use the predicted active site. So the active site in this figure, we can consider this as the prediction. And then we do what we call the docking. So basically, when you have the active site, it's not enough. You need to find the right conformation, like the right position of the molecule in the pocket. So we go through the docking, we to basically find the right conformation of the substrate when it will be bounded to the active site. And when the docking is performed, we compute the energy of the combination. So if we go here, we compute the energy of the enzyme and the substrate complex. And we compare this energy to the energy we will have obtained if we used the ground truth active site. So if I go back to this figure, for the perfect model, we will expect to have a straight line, like basically XYZ. So, but what we found is, for most of the predicted active site, we had an energy which is actually close, but not exactly, to the energy we obtain with the ground truth. So, in addition to the overlap between the ground truth active site and the prediction binding site, it is also important to measure the energy of the enzyme substrate complex you will obtain if you were using your method to actually predict the binding site of the proteins. So there's also one way to validate the model, like basically double check the performance of the model. So as the performance, they were not that exciting, but it was a good start, like to basically open the direction of server research. So one thing that we try is basically say we start with a random model. So the question we try to ask is what will be the prediction of the random model? So we basically have a sequence and we randomly pick some chunks of the sequence and consider this as the active site. So what is the overlap score of the random model with the ground truth? And we found that the random model wasn't that bad because it obtained 14%. And the other two model we should really consider in this plot is the Prot Albert and the Prot Bert, because this model have been trained on a sequence of proteins using language model. So we will expect this to we will expect the attention information learned by this model to contain the information on the binding side. So we also tested this model, and this model were not that bad. The overlap score, sorry, the overlap score were about 20%. And then the final, the ML based model, which is RX and Mapper, basically what the model that we trained, we observed that we were able to recover 52% of the actual binding site of the enzyme. But this was not enough compared to the database containing the homology information on the enzyme. So we didn't outperform the baseline, but this was an exciting result because first, the model was trained with an unsupervised method. So we wouldn't have expected the model to contain information on the active site, but this was, I would say, a milestone in predicting the active site of the protein. And also, one thing to stress out is this is a work done 3 or 3.5 years ago, and over time, the method has improved. And now we have model like AlphaFold 3, which is very good on this task. So also keep in mind that this is a work that has been done quite a while. So yeah, and there are several conclusions that we can draw from this work. And the first is using only the one-dimensional information, we can effectively extract three-dimensional information. As we can see, the amino acid sequence basically are only the sequence describing the information, and the binding pocket, when you visualize actually this in 3D, it's a region in the protein. So basically, we need the information, like the coordinate in the 3D space, to describe this binding pocket. And as I mentioned, there are other methods like AlphaFold that perform significantly better on this task. So if you are interested in predicting the active site or interested in the interaction between the enzymes and the small molecule, then you should consider up-to-date method. And one thing that we found when we were working on this is processing, like the amino acid sequence can be very long, and we found that processing long sequences was costly. But now I think there are breakthrough in the actual design of the GPUs and also how the attention mechanism run on these GPUs, like there are several works that try to actually encode, like have some processors that are designed to run the self-attention mechanism. So now we have some process like the flash attention, which basically try to rewrite the attention, like in the self-attention mechanism, like we basically try to rewrite the instruction at the GPU level such that we minimize some operation and the transfer between the memory. So this is one way to hasten the inference through a model using the self-attention. And over time, we also had sparse attention mechanisms that have been developed. So if someone is interested in using this, you can also extend this work with the sparse attention mechanisms. And as I mentioned earlier, we found that the performance of the model was very sensitive to, I'm sorry for the typo, was very sensitive to the tokenizer. So one direction that can be pursued is you can also try the tokenizer free language model, where, but by tokenizer free, it's not entirely free from the tokenization, but it's just you can use several tokenizer and then try to build the distributions over the tokenizer, and then you process, like you have a latent representation which is built up on the distributions of a different tokenizer. So it is also one way to reduce the dependency of the model on the tokenizer. So this marks the end of my presentation, and I am open to questions. Thank you.
Okay, thank you very much, Loic. Yeah, I'm just going to read the questions in the comments. I think like everyone can just type more questions in the comment. The first question we have is from Idris. He said, "We don't have a stop word or something like that. So how can we segment this sequence?"
We actually have the stop word. I didn't mention it here. When we describe the sequence, like between the first blue token and the purple, like there is a symbol, like that symbol separates the reactant from the enzyme. And between the purple and the second blue, I would say, words, we have another symbol which separates the enzyme from the product. And also at the end, we had a special token to mark the end of the sequence. So I think if you go to the GitHub that is mentioned in the paper, you will find all the implementation detail, but we do have an end of sentence sequence to effectively mark the end of the sequence, and also special tokens to differentiate between the react and the product, and also the enzymes.
Okay. Okay, thank you for that. So this now is a question for me. So from my understanding, it's like you have the molecules that are like in the SMICE representation. So they have like a different tokenization. And then you have the amino acid sequence that have a different tokenization, the byte pair tokenization you spoke about. So at
Yeah.
the end, like for the training of the model, do you just combine all these tokens like into a big vocabulary that's a mix of everything?
Yeah. For these different parts of the reaction, we have separate tokenizer, but at the end, we have a single vocabulary. But like we have a single vocabulary for all the reaction, but for each part of this reaction, we use a specific tokenizer. So yeah, at the end, we have a single vocabulary, but this vocabulary is made up of from two tokenizers.
Okay. Yeah, so there's one part I missed a bit in the presentation. So I understand like you use the language model training, like the mask language model training to kind of learn the embeddings. But
Mhm.
how exactly, I think you explained it a little bit, but I think I didn't understand properly. How exactly do you use the final embeddings to identify the binding sites? So
Yeah, if I go back to this figure, like if you take the transformer for example, you will have several layers and different heads at each layer, and each of these layer you'll have uh, that layer will predict the input, like the output of the inputs of the next layer using the self attention mechanism. So let's say I should have used a specific figure for this, but yeah, when we train a model using a mass language model, at the end, uh, to predict, like to actually predict the binding site, we do the inference on the model using a reactant and an enzymes. So when we do the inference, we only have the reactant and the enzymes, and we predict the product. And at each time we predict the product, so we choose a specific layer and head, and for that combination of layer and head, we analyze the attention matrix between the reactant and the enzyme. So here in the figure on the right hand side, you will have on the row the reactant, on the column you will have the enzyme, like the chunks of the enzyme. And for each of the reactant, we actually look at the attention matrix, and we take the chunks of the amino acid sequence that have the strongest attention weight. So this is how we do this for each atom in the reactant, and we collect all the active site for each of these atom in the reactant, and we consider this as the binding site. So this is basically how we do the inference after the training to figure out the active site of the enzymes involved in the reaction.
Okay, thank you for that. Then the other question that comes to my mind, like it's kind of like I'm also not like very familiar with this, but I did a little bit of research on the protein and the binding stuff. So like in your data set, did you consider like reactions with like having the same protein, like the same amino acid sequence, occurring like in multiple reactions?
Yeah. This is a very good question. When we constructed the data set, we consider also the reaction with the same amino acid sequence, because one amino acid sequence can have multiple binding sites, and depending on the reactant, um, the binding site that is effectively used in the reaction could be different from the binding site of another reaction. So we also make sure that when constructing the data set for a given amino acid sequence, we have enough reactant that will cover all the binding sites of the amino acid sequence. So yeah, we took this into consideration when constructing the data set.
Okay, okay, cool. Okay, so it means at the end of the day, you predict all the possible binding sites of that specific protein. It's not just like one protein, one binding site.
Yeah. It's not only one binding site, but I think the thing that we didn't do is during the inference, we did not differentiate between all the possible binding sites. So I think your point is interesting in the sense that one can be interested in figuring out all the possible binding sites, because what we did is we collect all this sequence, and we consider this as only one binding site. But at the time, it was a good starting point, but this is not actually suitable. Like we can push this forward in trying to conceive another method to actually differentiate between the possible binding site of a given protein, because now the current method will only predict one binding site, but on one protein, as I mentioned, we can have different binding site. So yeah, this is actually a good point for someone who wants to continue with this. So we can also be interested in figuring out all the possible binding site and also do the docking. Like we can find all the binding site and also do the same procedure here for each of the binding site. We do the docking, like we find the right position of the molecule and we compute the energy of the complex. And one can say we can pick, for example, if we are interested in um, figuring out the binding site that will minimize the energy reaction, and we can figure out all the possible binding sites, and then we do the docking. Like for each of the binding site we compute the energy of the complex, and then we pick the binding sites that minimizes the energy of the reaction. Yeah, your point is interesting and it can be used to further this research.
Okay. Yeah, there are not that many questions in the chat. Just had another curious question, like on the table with the overlaps, somehow I just feel like the overlap scores, they feel like they're correlated to the false positive rates. It's like when the
Yeah,
positive rates are increasing, like the overlap scores are also increasing. Like,
yeah, I think yeah, this was an important point that we found was these methods are not actually reliable. Like it was a good milestone in pushing forward the research, but we need to solve this. So I acknowledge that this is actually a problem. So because the false positive rate is also high, then it's hard to rely on this to, like, if we want to use it in industry, that would be actually very like it's not accurate and reliable. But as I mentioned, there are other methods that are actually very accurate. Like if you look at AlphaFold 3, if you already look at it, and for this task, it's actually quite accurate, and the false positive rate is very slow. Is very low. So yeah, at the time we built that method, we had this problem with the false positive rate, but I think over time there are some researchers that try to minimize this, and now I think we have a satisfying false positive rate. And I think I know people using this model in industry, and they are to some extent satisfied with the current false positive rate. But yeah, at the time we did this, we actually had a problem with this false positive rate.
okay. Yeah, just a follow up since you work at DeepMind. I know like like I was saw like the AlphaFold, like they do the structure prediction, but do they also actually have like the binding site prediction as well?
Yeah. I think the AlphaFold stream of work started with the structure prediction, but now I think it goes beyond this. The latest version not only focus on the structure prediction, but also the conformation of the molecule, like with the small molecule. Yeah, I think the latest version encompasses this. So yeah.
Okay, thank you. I don't see any more questions in the chat. I'm just going to ask you like a final question, like so now like what are you working on? Like you've no more continue on this work. Like what's your current research and like
Yeah, as I mentioned, the domain in which I working has been shifting quite a bit of time. So now I am working on chemistry, quantum chemistry and AI, basically running, yeah, try to understand the electronic system and see, like, basically try to understand this using AI and see how we can use it to do better simulation. So yeah.
okay, so there's another question here. Do you take into account the different actions between the molecules? Do you take into account the different action between the molecules? I'm not very sure. Yeah, but that's a question we have in the chat.
Uh, I
I think he
don't.
maybe I think he means reactions between the molecules.
Different reaction. No, I don't think we took. I mean, I don't quite get the question, but um, I think only from the one-dimensional information, like from the smalls representation. No, we didn't look at the actual interaction between the molecule. Like, no, I'm not sure we look at this information. Yeah.
Okay. And then there's another question from Wamba Naomi. Uh, she says she's a little bit curious about the data set size and the length of time required for training. So maybe you can just talk a
Yeah, I
little bit
think
about.
the data set, the training set has about 1 million reactions. And if I recall well, the length of the amino acid sequence, when it was tokenized, it has about 5,000 token. So I think in terms of amino acid sequence, we're about 30,000 amino acid sequence in the enzymes. And but yeah, the whole training set had about 1 million reactions. Yeah.
And in terms of training time and the size of the model, like
We use the Ericsson mapper was bird small, not small, medium. So I think it has about 500 million parameter. Yeah, and the training time 5 days. Yeah, because I did it for a long time ago. Yeah, but if I recall well, it took 4 to 5 days to train.
okay, yeah, that's quite
Yeah, but I
500 million.
think now there
It's
are.
still a big model, like it's
You
quite.
say?
I said 500 million parameters. That's still quite a big model. Like,
Yeah, it's still a big model. But I think now there are a lot of optimizations that have been done on the GPU. So I think it will take less time now, given the progress that have been made on the infrastructure side. So I will expect if we were reproducing the same experiments now, I will expect it to take less than a day to train.
okay,
Yeah, with a few resources. So yeah.
all right. Yeah, she says that that's a lot of resources. Well, yeah,
Uh
especially machine learning.
yeah, our grace.
Okay. Uh, actually had the question in mind. Yeah, so actually had the question in mind.
Okay.
So like the full sequence you use has like in the at the beginning of the sequence you have like the splice representation
Mm-hmm.
for the molecules. Then in the middle you have the amino acids sequence for the protein. But then
Mm-hmm.
at the end exactly like I'm still not very sure like what's there at the end
Is
because normally
the Please go ahead.
yeah because normally like what I know is like most now actually most of the time it's kind of like you have like a molecule and then you have like the protein. And then the binding, I'm more familiar with doing the docking and getting the output structure, not
Mm.
an output sequence. So that's why I'm confused. Like, what do you have at the end as for your output?
At the end, we have the smalls of the product, but we don't consider the enzymes after the reaction.
Okay,
So we only, yeah, as you mentioned, the first two parts were correct, and at the end we have the smalls of the product. And yeah, we don't consider the enzymes, and we only care about the smalls of the product at the end of the reaction.
okay, all right,
Yeah.
okay. So I don't see any other questions in the chat. Okay, guys, welcome to have like me give you 2 more minutes. Okay, now there's another question. Okay, to go from 3D to 1D condensed information, it is possible to use a latent space, I mean, making a projection of information in a reduced space and observing. Yeah, I think his question is a little bit like going from 3D information, from 3D to 1D. But actually, like here we're doing the reverse. Like you're going from 1D to
One day to
3D.
yeah.
Yeah, so it's kind of like, yeah, it's a little bit the reverse.
Yeah,
But I think
I think I'm not too much familiar with the biology stuff, but I think to go from 3D to 1D is much more simpler.
yeah,
Like
that's much more simpler. Yeah.
we don't need machine learning, like we don't need very complicated technique because I remember when doing this, at some point I had a 3D structure of the protons, and it was quite easy to go from 3D to 1D. Like there are some statistical tool that we use. It was actually very easy, but it's the reverse that is very complicated, like to recover the 3D structure from the 1D. But yeah,
Yeah, I think that's why the entire research is all about, like moving
yeah,
from the 1D structure to the 3D structure of the molecules.
yeah. Also because there is not a one-to-one correspondence. Like there's not a one-to-one mapping between like when you go from the 1D to the 3D, there are almost infinite possibilities. So yeah, but from the other way around is almost certain that you will have a handful of 1D representation if you have the 3D structure of the protein.
Okay, thank you. What other question do you have in mind? Uh, I don't have any specific question in mind. Mm. Okay, yeah, I mean, like there are a lot of questions that are coming to my mind, but they're just like all messed up around. Like, and in
Yeah,
terms of like in terms of the molecules representation, like I guess in this case, because you did not do like a next token prediction, you did like a max token prediction. Did you have like issues with using the SMICE representation for molecules? Because like
like
for some studies, like for some specific studies in molecular generation, the SMICE representation sometimes seems to be difficult to use for machine learning models. So like in your studies, like something you had to like consider, or
I think we
like
didn't
issue.
consider this factor, but I think when you said there are some difficulties with the small, what do you mean concretely?
I think most in for studies that focus on molecular generation, like
Yeah, I
designing
see.
new molecules, whenever they use SMICE representation, they generally see a lot of difficulties in actually generating valid enough molecules.
Yeah, yeah, I see. Yeah. From the small, um, yeah, I think for the molecular generation, the small is not enough because sometimes you need also to look at the torsion angles of the molecule, see if the molecule you generate is stable. So what we do is, I think we start from stable molecule, like from the 3D representation of stable molecule, and then we get a small. So we didn't do the reverse process where we try to generate the molecule. So I think what you do is, like what you said, will be valid. I mean, it is valid, but I think in our context, we would have cared about this if we were also going from the 3D, like from the 1D of the molecule to the 3D for the molecular generation. This is where we will have to deal with this problem. But I think to make the data set, we went from stable molecule in reaction, like stable conformation, and then we get the small and we train on that. But if we were interested in the other way around, where let's say in if we want also to if we wanted to see how the atoms of the molecule interact in the reaction. So let's say in place of the enzyme, we had another molecule like reactant, and we had a product. So in that case, we will have also like it might be good also to look at the conformation of the molecule, basically look at if the generated molecule is stable. But yeah, we didn't look at this component because we thought at the time it wasn't relevant for the work. But yeah, for a broader research, we should take this into consideration. Yeah, I agree.
Okay, thank you. I don't see another question in the chat. My final question is like the P farm based method you have like in this table. Is that actually like a model, or it's just like a database? Like exactly, I didn't really
Yeah, I think
understand it.
is a database. Um, I think is a collection of enzymes or proteins with the active site of this protein. So I think it basically work. If I recall well, it's just a database, and then it has for certain molecule the patterns that it's identified as the active site. So it's just a database, and if you have a sequence, I don't know if I find the website of this, I will send you later, and if you can share with the other, that'll be good. But in that, like basically, what the website is just the interface, and under the hood there is a database of amino acid sequence and the patterns that are recognized as the binding site. And whenever you query that database with a given amino acid sequence, then they will find, given the recorded binding site, what could be the potential binding site in your amino acid sequence. So I think it's just a database, and then they use some overlap process to figure out the binding site on your query.
Okay. All right.
Yeah.
Thank you very much, Loic, for making the time to present on a Saturday evening. And thank you, everyone, for the listeners. I think we're going to end it now. And everyone have a nice weekend.
Thank you, Ulrich, for hosting me. I'm very pleased to be here and share what I've been working on. And I hope I will have the opportunity to share if I continue, like, if what I'm working on actually get publicized. Maybe if there is a slot, I will be happy to come here again and present it.
Okay. You're welcome.
Yeah.